As we go into topic 3 of chapter 3, we're going to take a look at applications of linear functions, and we're going to revisit something we did back in section 1.2. That is the cost function and the revenue function. So a quick definition again: the revenue is the money that you will sell each item for, and you multiply that by the number of items, which is usually your X value. So this will give you money in. Now for the cost function, we said there were fixed costs. That was your capital investment. And then the items that you are producing have immediate material cost. Those are the variable cost. And for each item, it's going to cost this much. So you might recall we said we would sell something for, let's say, $2.50. And then we had some fixed costs of, let's say, $4,000. This is what we had before. And then this was revenue, that when we sell each item, we sell it for $4. So we'll be looking at that in some detail as we go through the pages of this section. And we do want to define what profit is. The profit function is if you have all the money that you take in and you subtract the cost, then you have your profit. In your text, they do give you some background information of what cost analysis, the building, the machinery, the real estate taxes, product design. Fixed costs include, those would be fixed costs, and then variable costs, labor, materials, shipping, and so on, depend on the number of items made. So, starting off, if you wanted to find out what were your fixed costs, if you have this cost function here, and you don't sell any items, your X value would be 0, then this is your fixed cost. And you recall that on a graph that we did make before, let's make a nice graph over here, that this was your revenue function. You started at 0, but then your fixed costs were in here somewhere, and we were looking for where these lines would intersect, and that would be our break-even point. And then selling one more item, you were up then in the profit area. Now in example 1, we're looking at an anti-clot drug can be made for $10 per unit. The total cost of production of 100 units is $1,500. So what would be the cost function in its linear form, that is the equation? Well, we said throughout this we're going to use something very similar to slope-intercept, y equals mx plus b, where b would be our fixed cost, and then the slope would be our individual costs, and x is the number of items. And we said we can convert the y to, in this case, cost function c of x. So if we know our total cost for the 10 units, we're going to sell each unit for $10. That's what it, we'll get our vocabulary here. We are given that m, the cost per item, which is the slope, is $10. So this is our rule. We're substituting the 10 for the M. Now we know it cost $1,500 to produce 100 units. So there's 100 units, and somehow that will equal our total costs of $1,500. Well, we know we have to figure out the B part then. What is our y-intercept in a sense? So we're going to produce 100 units at $10 each. That gives us 1,000. 1,000 plus B is our total cost, 1,500. So B then would be 500. And now we can put it in our cost function. That it's $10 to produce each unit, and then our fixed cost would be 500. So this is the rule. The equation in slope-intercept form, this is the rule. As we put in our x values, the number of items, we get our cost. Now, what are the fixed costs? Well, once we see it in this form, our fixed cost would be $500. Whatever our y-intercept is, that's our fixed cost. Now they're introducing a modification of this formula somewhat, and this is average cost. Now we know that as we produce more and more items, generally the price goes down. This is as you produce lots of them, it costs less. Well, that's because of you're diluting this fixed cost a little bit more. So the formula they're giving, they're putting this bar over the C, which is the indication of average. So average cost would be total cost times X, the number of items you're selling, divided by the number of items you are selling. And we're going to see that in example 2. So they want us to find the average cost of producing 100 items, and then later 1,000 items of anti-clot drug. So this is our basic cost rule or function. And if we are producing 100, then C times 100 divided by 100, and we said it cost $10 to produce 1 unit, and we're adding, of course, the y-intercept here, the fixed cost of 500. We then get 1,000 plus 500 is 1,500 divided by 100 units that we're producing. This gives us an average of $15 per unit. Now, if we're going to produce 1,000, we want to find the average cost of 1,000 units. We're going to multiply against our cost by 1,000. So 10 times 1,000 plus 500. Now notice this amount hasn't grown, hasn't gotten larger, but this amount has gotten larger. So in a sense, this is diluted because we're making so many more. We get this on the top divided by 1,000. We now find that our average cost per unit is only $10.50. Again, because you're producing more items and making this a smaller value per item. That's what happens. Now, as we continue, we're looking at what is called rate of change. And there is our rule, our function of slope-intercept. So what determines your rate of change here? Well, it's the slope. So whatever the cost of a particular item to make, that is your rate of change. And again, in the B position, this would be your fixed cost. Now, what we're going to take a look at now is linear depreciation. Now, if something depreciates in value, like an automobile, which we will talk about here, we're going to see a curve, or a line, I should say, that starts high, and through time, the line goes in a negative slope direction. We call that depreciation. And we can use this slope formula if we have linear depreciation, that is, straight line depreciation. Now, in the automobile business, Kelley Blue Book is sort of the Bible for looking at values of various cars. And they're saying that a Ford Mustang two-door convertible today is worth this much, and in 2 years would be worth this much if it's in excellent condition with average mileage. Now, assuming that it's linear depreciation, find the depreciation function for this car. That is, find the rule. And you might say, well, how would I do that? Well, you're going to use two ordered pairs that you're going to start today, which is 0, and its value is 14,776. That's one ordered pair. And then in 2 years, so time is X, it's going to be worth 10,600. Now, with 2 items of data, we can use this to determine our slope, well, the slope formula. If this is our slope, and again, we're putting it in function, that will be a negative 2088 x. Now, interestingly, I don't know if you notice this, but this is in the y-intercept form, 0, b. Well, what would our y-intercept be? It's going to be this. So there is our linear depreciation function here. Now, what will the car be worth in 4 years? Well, in this case, we're going to put a 4 where the x is. This would be a negative value. We will then subtract that from this, and we would see that it's written below $6,424. So this is what happens to automobiles. Unless they are in mint condition and somehow famous, and then as they get older, they actually are worth more money to collectors. And our last item here, C, at what rate is the car depreciating? Well, again, this is rate of change, and that happens to be the slope here. And what does that mean? Well, each year your car will lose this much in value. Now, as we continue, they're talking about another term that in economics is used, and that's sometimes called marginal cost. Well, marginal cost is actually just another name for slope, depending about what you're talking about. And these are the marginal cost. And we'll see that in our next example. So, an electronics company manufactures handheld PCs. The cost function of one of these models is this. Now, as we look at it, this is in slope-intercept form. What are our fixed costs? Well, we said it's our y-intercept. And what would be our marginal cost? Well, it would be the slope here. And they're showing what are the fixed costs. Well, if you're producing 0, it's 160 times 0. It's just going to be your y-intercept. And what are the marginal costs? Well, it costs 160 to produce an item. So our marginal cost, as we say, is the slope. After 500 units have been produced, what is the cost of producing one more? Well, here they're going through quite an elaborate calculation. They're going through 160 times this, plus that is this. And then they're just adding one more to this 50,000, and you get this, and you subtract them, and it's your marginal cost, your slope again. So the cost of producing just one more item is the marginal cost. In example 5, we're looking at an energy company that charges each customer a basic fee of $15.11. This is usually a month. Plus this much per kilowatt hour. Now, assuming they're going to have this many customers, find the company's revenue function. Well, the revenue function is going to be, let's put it out here, how much are they charging each kilowatt hour? Well, this. So that would be 0.0333, and this will be times the number of kilowatt hours plus, now here each of these 700,000 are paying this much as a basic fee, which they're showing here, which give us, in a sense, our fixed income. So this is sort of a combined revenue function. It's not just what they get per kilowatt hour, but also this minimum fee they get from each of the clients. So this is your revenue function. Now, what is the marginal revenue? And again, when it's in this form, we said marginal revenue was the slope. Remember, this is our M value in the slope-intercept form. So in this blue box, they're sort of comparing linear cost function in slope-intercept form with linear revenue function in slope-intercept form. And you might say, well, how come there is a, well, we know that B is our y-intercept and our fixed cost. Here, our D, which is in the y-intercept area, is the price that each customer has to pay to keep up the service before they use anything. So that's added to their revenue here that we described up there. So this was something we did earlier, and we'll repeat it another time here, that generally speaking, our revenue starts at 0 and goes up like so. And then when we have our cost. This has some y-intercept value there, fixed cost, and then as these lines cross, we reach our break-even point. So we did one like this earlier. Let's take a look at it. A company manufactures 42-inch plasma HD TV and sells to retailers for this. The cost of making these is given for a month by this cost function rule that is going to have this materials cost of $250 and then fixed cost of this. Now, what will be our break-even point? And they're asking us first, though, what is the revenue function? What is that rule? Well, that's going to be R of X will equal what you sell each TV for here, $550 for each unit sold. And that's what they give us here. Now, what is the revenue from selling 600 TVs? Well, for the X here, you plug in your 600 and you just do the multiplication, and it would be $330,000. Well, find the profit now from this function. And remember, we said the profit function was profit equals revenue minus cost. Well, we have to figure out our cost function, which we have there, and let's take a look at it. So there's our formulas, and there's our revenue minus the cost. Now notice when we remove this parenthesis, this then becomes negative, and so does this become negative. So we subtract the 250 from 550 and get 300x minus this. So we want to, that would be our profit statement. And again, we have to see how many we need to sell to break even. And then when we sell one more, we start to make a profit. So in letter D, what is the profit from selling 500 TVs? So if you put 500 there, 300 times 500, when you get this value and you subtract your fixed cost, you end up with a negative number. So by selling just 500 of these TVs, you haven't reached your break-even point. You're down here somewhere. So that is a loss. The company only makes a profit if they go beyond the break-even point. So you might say, well, how many do they have to sell? Well, you might try 600 there. Then you would make a profit. And I spoke too soon. I was shooting from the hip on that one, because how would we find the break-even point? Well, again, we get the revenue function equal the cost function, solve for x, and we get x is 710, not 600 as I just threw out there. And how many would you need to sell to make at least a little profit? Well, one more than that. So 711 to make a profit. Okay. Now this is a nice diagram. In this area, anything that occurs in this area is a loss. And then anything that occurs up in this area is a profit. And your point of break even is you will sell 710 units, bringing in this much money. 711 now brings you into this blue area up here, which is your profit area. Now here they're introducing a little shot of what a calculator screen might look like, graphing calculator, showing you the lines of intersection at the break-even point and the graph we just looked at. All right, now another area that we're going to take a look at is what is called supply and demand. Now, in any business, if you produce something and initially the costs are quite high, then people aren't going to buy it right away. A good example of this is, maybe 10 years ago, I bought a flat screen TV, 28-inch, and it was $1,200. If you look at a 28-inch screen now, it's going to be maybe $250. And the large screens, the 40-inch, the 50-inch, the 60-inch, were quite expensive. Now, because again the supply is ample, the prices have gone down quite a bit. So this is what producers are often thinking about. Depending on their supply, what will be the demand and what would be a reasonable price for them to make a profit. So this is what we're going to look at here, and we will use P for price and D, we'll use P for price and Q for quantity. Okay? And we'll discuss this in more detail later chapters, but we'll take a look at now at example 8. Now, folks that are in economics, study this and can develop rules for this. And let's take a look at this one. Studied supply and demand for aluminum siding and has determined that the price per unit, P, and the quantity of demand, Q, are related by this linear equation. So they're going to have to give you the equation, which is nice. And of course, I taught in the past we had to find the equation. That would be similar to, having data and then using the point-slope form, but here they're giving us the formula. Find the demand at the price of $40 per unit. So price, P, is $40. So there's our formula. We're substituting the P with 40. We go through it, and we end up with Q, which is the quantity, is approximately 26 2/3. So at the price of $40 per unit, the demand will be 26 2/3. That is 80 thirds. Find the price if the demand is 32 units now. Well, we're going to put 32 units there, and let's move it up to see it. So 32 units will be our Q value. So where the Q is, we substitute 32. Notice this cancels nicely. 4 goes into there once. 4 goes into there 8 times. -3 times 8 is a -24. So the price would be $36 when the demand of 32 units. Now they're asking us to do a graph of this. Well, notice, in a sense, we could reposition that into P equals a negative 3/4 Q plus 60. So just to mentally sketch this a little bit here, our y-intercept is going to be at 60, and this is negative slope. So this graph will look something like that. Oh, my diagram wasn't too bad. Again, you saw that the slope was negative here, and the line, of course, is going down. And notice the 2 points. When it's 40, we get this value, and then when it's 36, we get this value. So those points, of course, are on the line. So again, we don't see this, but for letter D now, at what price of 30, at what quantity is demanded? So you would go the price of 30 up on the vertical axis, the y-axis, then go over and it would give you 40. At what price will 60 units be demanded? And you would go to the price of 60, so the quantity is 60 down here, and you would go up, and it looks like $15 per unit. And what quantity is demanded at the price of $60 per unit? Well, if you go there, and I think we can go back up here. Yes, there we go. At 60, we have sales of 0. There's a 0 there because it's just too expensive. People aren't going to buy it. Now, there's always somebody going to buy something, but that's just going along with what they have here. Okay, let's take a look at example 9. Now, in example 9, they're using a similar example from 8. And they conclude that the supply Q of siding is related to its price, P, by the equation, and this is a price function, that it's 85 cents per unit. So find the supply if the price is $51 per unit. Well, maybe that's not 85 cents. That's just the relationship. So price is 51. So 0.85, divide both sides by 0.85, you get Q. The quantity is 60. So if the price is $51 per unit, then 60 units will be supplied to the marketplace. Now, I don't know if you're noticing this in this formula. This again is the slope. So this one's, as we look at it, is going to be positive slope. Well, it's actually coming from 0. And there's a better graph of it. And then we saw the other one. So there's going to be like an ideal point where we have this negative slope and this positive slope. We'll be getting to that. We're building up to it now. Find the price per unit if the supply is 20 units. So again, 0.85 times 20 is 17. So if the supply is 20 units, then the price is $17 per unit. And then graph this equation. So once again, very similar to the one I just gave you, and both of these points are on the line. Use the graph to find the approximate price at 35 units will be supplied. So this one we're going to look at 35 units, which is right about there. And it looks like 35 is right there. So it looks like the price will be about $30. Ah, good. And again, citing it from the graph, we don't get the exact amount, but doing it this way, we do. Now, you probably anticipated that they were going to put both of these graphs on the same quadrant, and that's what we see here. This is demand, and this is supply. And they're asking us whether there is a surplus or a shortage of supply at a price of $40 per unit. So P is 40, so we make this dotted line. Remember, this is sort of the equation y equals 40, which is a horizontal line. And notice what they're saying. This point lies above the demand graph, so supply is greater than demand at the price of 40. And there is a surplus of supply. Now, what we often shoot for here, and they're introducing this, is what we call the equilibrium point. Again, manufacturers are always, they don't want to produce too much or too little. They want to keep it going, hopefully at a reasonable price. Well, this is called the equilibrium point, and that is where these lines intersect. And we talk about the equilibrium quantity. Well, quantity is about, would you go along with 37.38 or so? All right. Well, what would be the price then? Well, about $33 maybe. Let's see what they say. Well, again, if we put values and one side equals the other, we're sort of looking at the break-even point. The quantity, as we said, is about 37.38, comes out exactly 37.5. And the price, we said about $32, $33. Again, it's hard to read, but you're getting some exact information here. So the coordinates for price is about $31.88, and the quantity or number of units about 37.5 is our equilibrium point, or as we used to call it, our break-even point. Okay, well, you'll have some practice and quiz me's to do as we continue on Chapter 3.